Howdy. This video is on the wave nature of matter and Heisenberg's uncertainty principle. Wave-particle duality of really small things and Heisenberg's uncertainty principle are related to each other and are indicative of the composition of energy and matter. They also illustrate how little stuff behaves very strangely. After watching this video, you should be able to describe how light, electrons, atoms do not behave like apples, be able to calculate the wavelength of a moving object, be able to calculate the minimum uncertainty in position or momentum given the other. And so before quantum mechanics, physicists made the mistake of believing that things at the atomic level behave like things at the macroscopic level. They believed that electrons and atoms behave like little apples, that they followed Newtonian physics. It's hard to accept that things at the atomic level behave differently, very, very differently than things at the macroscopic level, but it is true. But if we think about it another way, there is no reason to believe that light, electrons, and atoms should behave like apples, and they do not. Classical or Newtonian physics works well for stuff in the macroscopic level, for apples. Quantum mechanics is necessary to describe the submicroscopic, the atomic level, electrons, light, atoms, molecules. And so they behave very, very differently, and I'll try to convince you of this during this video. It's also kind of interesting. We can also even think about these Newtonian physics versus quantum mechanics on a philosophical level. And so according to Newtonian physics, if the position momentum of a particle and the forces acting on the particle are known, then you can calculate the position of that particle and momentum any time in the future. And so you can imagine that if we knew all the positions and momentums of all particles in the universe, we could calculate the universe at any time in the future. And so basically, according to Newtonian physics, the future is already determined, it's already been defined, and there is such a thing as fate. Now, according to quantum mechanics, it's a little bit different. We calculate probabilities, and we cannot know position momentum of a particle with complete accuracy. And so according to quantum mechanics, there is no such thing as fate. Quantum mechanics is necessary to describe the atomic level. It was developed between 1900 and 1925. We see both electromagnetic radiation and matter exhibit properties of both waves and particles, hence wave-particle duality. Energy is quantized. Only the probability of an event occurring can be determined. There is not always cause and effect. There is no fate. The position and momentum of a particle cannot be determined simultaneously with complete accuracy. And so this is referred to as the uncertainty principle. And so historically, we can think about it. Newtonian developed classical physics around 1686. Dalton developed the atomic theory between 1803 and 1807. And again, it's very impressive. Dalton's atomic theory and the periodic table developed based on purely macroscopic observation of reactions, and they're both consistent with the structure of atom, and quantum mechanical description of the atom developed much, much later. 1895, discovery of X-rays. 1897, J.J. Thomson measured the ratio of the charge and mass of an electron. 1900, Planck postulated the quantization of emission absorption energy to explain blackbody radiation. Blackbody radiation could not be explained using classical physics. 1905, Einstein proposed that radiation itself was quantized, called photons, to explain the photoelectric effect. Now before that, the photoelectric effect could not be explained with purely classical reasoning. And Einstein earned his Nobel Prize for his explanation of the photoelectric effect. In 1909, Millikan used the oil drop experiment to calculate the charge of an electron. 1910, you have the existence of the nucleus. Rutherford proposed the existence of the nucleus. 1914, Bohr's quantum model of the atom. 1919, the proton was finally discovered by Rutherford. 1924, de Broglie hypothesized matter waves. 1925, Heisenberg and Schrödinger independently formulated quantum mechanics. It's kind of interesting. Heisenberg used matrices to describe quantum mechanics, while Schrödinger used differential equations, and it was seen a year later that the two were equivalent. 1926, Heisenberg developed his uncertainty principle. And so you should notice that Dalton developed his atomic theory, and the periodic table was developed before the structure of the atom was known. Those two were developed purely by macroscopic observations of reactions. But we'll see that they're completely consistent with the quantum mechanic theory of the atom, quantum mechanic picture of the atom. Now, quantum mechanics is not intuitive, okay? We're used to apples, we're used to water, we see waves, we see particles. Quantum mechanics, it's very, very different. Bohr is quoted as saying that anyone who is not shocked by the quantum theory has not understood it. Bohr developed the quantum theory of the atom to describe the absorption spectra of hydrogen atoms. Einstein's quoted as saying that God does not play dice. Now, I think this is a reference that Einstein didn't like the concept that with quantum mechanics you talk about probabilities, you don't talk about certainties. And Feynman's quoted as saying that I think I can safely say that nobody understands quantum mechanics. Now, what I think Feynman was getting at is that we can do the math. There's equations. We can solve the equations, and we can calculate things, and the calculations always turn out right as long as we don't make a mistake. But it's hard to have a picture in your head of what it actually means. The math is right, but the picture is very difficult. So one example of that would be in terms of momentum, in terms of light. And so if light is like a particle, does it have momentum? And so light particle is called a photon. Does it have momentum? And so in Compton scattering, X-rays, relatively high energy electromagnetic radiation, high energy light, collides with an electron. And what we see is that when it collides with the electron, it actually causes the electron to move. It imparts momentum, and its momentum changes. And so how can a photon, which has no mass, have momentum? Well, in quantum mechanics, for really small stuff, we actually define momentum a little bit differently. Macroscopically, momentum is mass times velocity. And so if we think about momentum as energy divided by speed, then we get that Planck's constant times frequency divided by speed, and so Planck's constant divided by the wavelength. And so in quantum mechanics, we can actually define the momentum in terms of the wavelength. And so Compton actually won the Nobel Prize in 1927 for showing that photons had momentum even though they have no mass. And the way this experiment works is by measuring the change in the wavelength of the scattered photon as a function of the angle, you could actually show that the momentum was conserved. And so the photon hits the electron, transfers some momentum to the electron. Its momentum is reduced. By looking at the wavelength of the scattered photon versus the angles, you can actually see that the momentum is conserved. Kind of freaky. Photons have no mass, but have no mass, but do have momentum. Now, you cannot measure zero mass, but experimentally it's been determined that the mass of a photon is less than 10 to the minus 51 grams. That's the upper limit. And so if photons have no mass, how can they be affected by gravity? We know that light will actually slightly bend in terms of around a planet. And the reason for that is that according to general theory of relativity, a star's mass distorts the space, and the photon's path changes because space is curved. And so even though photons have no mass, they're affected by gravity, and they do have momentum. A little strange, something we don't expect. And so when we think about electromagnetic radiation, it actually is characterized by wave properties and particle properties. And so Einstein, to describe the photoelectric effect, said energy of a photon of a single particle of light is equal to Planck's constant times frequency. And so to me, that's really kind of interesting. You have energy of a photon, so basically a particle property, is equal to Planck's constant times frequency, where frequency is a wave property. Now, we also have that the wavelength times frequency is equal to speed of light. And so we get that the frequency is equal to speed of light over wavelength. So that gives us energy of a photon is equal to Planck's constant times speed of light divided by the wavelength. Now, if we set that equal to mc squared, so we have Einstein's equation equals mc squared. We have from light equals hc over lambda. And so it should be mc squared equals hc over lambda. Now, this is not going to be a strict derivation, but it's kind of cute and can show you how you can get the de Broglie equation for matter waves. And so we have mc squared equals hc over lambda, divide by c both sides, gives us mc equals h over lambda. If we solve for lambda, we get the wavelength is equal to h over mc. And so in this case, c is not speed of light, but we have the wavelength is equal to the mass over the speed. And so this is actually the de Broglie wavelength. This is the wavelength for matter. But again, please remember, it's wavelength equals Planck's constant divided by mass over speed. And so in 1924, de Broglie proposed that all moving objects had wave properties with a wavelength equal to Planck's constant divided by mass over speed. And so if we think about it, having an electron gun and we shoot it at a foil, now the metal foil has atoms, obviously. And what happens is the electrons will get diffracted by the atoms, and you'll get a diffraction pattern.
Electrons have wave properties. If we shoot a beam of electrons through thin metal foil, the atoms of the foil cause the waves to interfere with each other. The interference, or diffraction pattern, can be recorded on photographic film as a series of concentric circles.
And so it's really kind of cool. If we know the speed of the electrons, then we can actually calculate the wavelength of the electrons. If we then compare the wavelength of the electrons to the separation of the lines in our diffraction pattern, we can actually get the distance between the atoms in the metal foil. But the only reason this experiment works is because electrons have wave-like properties, and we can actually define its wavelength. Now, only small things have wave-like properties, and so a baseball at 100 miles per hour would have a wavelength of 1.3 times 10 to the minus 32nd centimeter. And so that's so small that you'll never ever see a wave-like, or be able to measure wave-like properties for a baseball. Only things at the atomic level, molecules, atoms, electrons, will we see wave-like properties. And this is very helpful when we talk about microscopy. And so typically the resolution of a microscope is set by the wavelength of what you're using. And so for a light microscope, you can clearly resolve objects down to about 200 nanometers. A nanometer is 10 to the minus 9th meters. So that means you can resolve bacteria and mitochondria. And so the light microscope is typically limited to the wavelength of the light. And so 200 nanometers for a light microscope. Now for an electron microscope, the wavelength of the electrons depends on the speed of the electrons. And so the faster the speed of electrons, the smaller the wavelength. The smaller the wavelength, the higher the resolution. And so it sounds kind of backwards. Higher resolution means you can distinguish between closer objects. And so again, faster electrons leads to smaller wavelength and hence higher resolution. And so you can actually get much higher resolution using an electron microscope than you can actually do using a light microscope. And so for electron microscope, you have a source of electrons, and then you use magnets to actually focus those electrons, and then it hits the sample, and then you have a detector to measure the scattered electrons. And so for higher resolution, it means you need smaller wavelength, and so you need faster electrons. And so with an electron microscope, you can actually get much higher resolution. You can resolve things that are much closer than you can do with a light microscope. And so a light microscope, you're looking at something like on order of 200 nanometers. For an electron microscope, you're looking at things down to a nanometer. And so if you want to resolve two atoms that are 1 nanometer apart using an electron microscope, how fast do the electrons have to move? Now, if you assume that the resolution of the microscope is equal to half the wavelength, which is relative, then you can actually calculate this out. You also have to remember that a joule is a kilogram meter squared per second squared. And so again, assume the resolution microscope is equal to half the wavelength. And so the wavelength is equal to 2 times the resolution. And so if our resolution we want is 1 nanometer, the wavelength will be 2 nanometers, or 2 times 10 to the minus 9th meters. And so we take wavelength equals Planck's constant divided by mass and speed. We solve for speed. We get speed is equal to Planck's constant divided by mass times the wavelength. And so Planck's constant is 6.626 times 10 to the minus 34th joule seconds. The mass of electron is 9.1 times 10 to the minus 31 kilograms. And our wavelength, again, is 2 times 10 to the 9th meters. Now, joule is a kilogram meter squared per second squared. And so if we plug in kilogram meter squared per second squared for joule, we can see that kilograms cancel with kilograms. One of the meters cancels with the meter. One of the seconds cancels with seconds. And we're actually left with units of meters per second. And so if we can get the electrons to move at 3.6 times 10 to the 5th meters per second, we should actually be able to resolve two atoms that are 1 nanometer apart. Really kind of cool. And again, just a result of electrons having wave-like properties. And so example of a SEM, scanning electron microscope, of a fly's head. Here we have white blood cell, platelet, red blood cell, a flu virus, the deadly Ebola virus. Here we have hafnium oxide nanocrystals. And so notice that the line is 2 nanometers. And so you're actually able to resolve individual atoms. And so that's what those white dots are. Here we have magnetite monocrystals. And in this case, the line is 5 nanometers. And again, those white dots represent individual atoms. And so all this is possible because electrons have wave-like properties. Now, can the quantum mechanical description of physical reality be considered complete? And so this is a question that Einstein spent the latter part of his life thinking about. You know, again, he's quoted as saying that he didn't think that God played dice, and that he didn't think quantum mechanics was a complete description of physical reality. In some ways, people think that quantum mechanics might conflict a little bit with relativity. And so Einstein used to think about thought experiments trying to find inconsistencies with quantum mechanics. And so one of his thought experiments, one of the more famous one, was in this Phys-Rev paper. And so the authors Einstein-Podolsky-Rosen, and so EPR for their initials. And it became referred to as the EPR paradox. And so this was Einstein's thought experiment. And so you have a pion. And when the pion decays, it produces an electron and a positron flying in opposite directions. And their magnetic moments are pointing in opposite directions. Okay? Now the direction of the magnetic moment is undefined until measured. Now the paradox part becomes when you think, okay, you let the electrons and positrons, the electron and positron, fly really, really far apart. Now until you measure the magnetic moment, it's undefined. But as soon as you measure the magnetic moment of one, the magnetic moment of the other one, the orientation, is defined. Now the reason this is a paradox is because if that distance is large and it's spontaneous, it seems to contradict Einstein's theory of relativity, which says that nothing can travel faster than the speed of light. But this experiment has been done, and it does spontaneously. Once you measure one, the other one's spontaneously determined. But Einstein referred to this as spooky action at a distance. It seems very strange, but again, it's how the world works. Another one that's really kind of strange is Heisenberg's uncertainty principle. And so in quantum mechanics, there are pairs of parameters that cannot be known with complete certainty at the same time. So for example, position and momentum along the same axis cannot be known with complete accuracy at the same time. But there's a couple different pairs that cannot be known with complete accuracy at the same time. And so the uncertainty in x, delta x, times the uncertainty in momentum, delta p, is always greater than or equal to Planck's constant over 4 pi. Now I want you to understand what this means conceptually. It just means you can't have complete certainty in position and complete certainty in momentum. But this illustrates why electrons cannot orbit nuclei in well-defined patterns, because there's always going to be uncertainty in either position or in terms of momentum. Now a nice demonstration of this is shining laser light through a small opening and making that opening smaller and smaller.
Heisenberg's principle indeed is very, very non-intuitive. Frankly speaking, I'd call it bizarre. But you can see it at work. Suppose I have a laser beam here, and I use laser beam because that's right, but I could use any other light for that matter. And I make here an opening, a slit, a vertical slit. And here goes the laser beam right through the slit. Light goes on, and here I project this onto this wall or screen, projection screen, and what do I see? Well, you see exactly what you predict. You see here this laser spot from this beam. But now I'm going to make this vertical slit narrower and narrower and narrower. What now are you going to see? Well, you're going to see exactly what you predict. You're going to cut off the edges of the circle, and the spot gets narrower and narrower and narrower. But now you come to the point that this narrow slit, say, is only 1/100th of an inch wide. And now Heisenberg's principle comes in. Because now you know so precisely in the horizontal direction where the light is, that as it emerges from this slit, the direction of the light is no longer determined according to Heisenberg's principle. And so now what you're going to see, it's going to spread out in the horizontal plane, and therefore what you're going to see on this projection screen is going to get wider. Extremely non-intuitive. Because what am I doing? I'm making the slit narrower and narrower and narrower and narrower. And what do you see ultimately? That the beam horizontally becomes wider and wider and wider and wider and wider and wider and wider. Now that is very non-intuitive, but it's the way the world works.
And so it's very strange. You can think about the experiment in terms of wave-particle duality, of the wave nature of light. You can also think about it in terms of Heisenberg's uncertainty principle. As you make that slit narrower and narrower, the momentum in that dimension becomes more and more uncertainty, and so you have an increased spreading out. And so quantum mechanics, very non-intuitive, very strange, but we need it to understand atoms, electrons, and molecules, and it's just how the world works. So I hope this was helpful. Please enjoy chemistry.